Ladies and gentlemen, let's continue with our module in heat transfer. We are using the textbook of Cengel and Ghajar. We are busy with chapter 9 on natural convection. With the previous lecture, we've looked at the mechanism of convection, and I've introduced to you the Grashof number. So let's continue with the Grashof number and what it means to us. But before we do that, let's just first look at the Reynolds number. So the Reynolds number is equal to rho Vd divided by the viscosity, and the Rayleigh number is equal to G multiplied by beta, temperature of the surface minus the free stream temperature, the characteristic length to the third divided by the kinematic viscosity square. The Reynolds number is the ratio of inertia forces to viscous forces, and the Rayleigh number is buoyancy forces divided by viscous forces. So they represent different things, and the very important thing that you should notice is that in the Reynolds number we've got velocity. In the Grashof number there's no velocity at all. Why? Because in many natural convection problems, normally the velocities are extremely low, the order of 0.01 meters per second, etc. So therefore the Reynolds number doesn't really play a big role. And for that reason, as we've used the Reynolds number for a flat plate, transition occurred typically at 100,000. Okay, so that is the Reynolds number. For buoyancy type of problems, for a flat plate, it is a Grashof number of 10 to the 9. If it's smaller than this, then flow would be laminar. More than that, it would be turbulent. In tubes, we know it is equal to 2,100 approximately, the Reynolds number. While for Rayleigh numbers, it is more complex. And if you want that result, you can go and look in Meyer and Everts 2018, and there you will get the correlations that will determine when the flow changes from laminar to turbulent in a circular tube, as well as the so-called mixed convection characteristics. In terms of forced convection and mixed convection, it is the easiest to illustrate it with a hot circular rod that has been heated, and we're going to look at 3 different scenarios. So it is heated, or its temperature is much higher than that of the environment. Firstly, if it is in the environment and there are no external convection, then the flow patterns would typically do something like that. And the velocities are very, very small, and this is natural convection. Or NC. For short, natural convection. In these cases, the Grashof number divided by the Reynolds number squared is typically much larger than 1. Therefore, that is typically the criteria that we can use. Now, let's suppose we put a fan here and we force the flow over this heated cylinder. The flow patterns is typically going to do something like that. And for these cases, the Grashof number divided by the Reynolds square would typically be much smaller than 1. And this is known as forced convection. Natural convection and forced convection. Now, the next possible scenarios is one in between. So here we've got a fan, but now we've got a very small fan there. Okay. Very small one. There's a fan, so it is sort of forced. What's going to happen now? The natural convection is going to have an influence on this problem. Let me just make this a little bit smaller so that I can have some more space. So there it is. What's now going to happen is the flow is going to do something like that. Okay. And this is called mixed convection. Or MC for mixed convection, and that one FC for forced convection. I'm going to use that a few times. NC for natural convection, FC for forced convection, and MC for mixed convection. And for this case, we've got the Grashof number divided by the Reynolds number square. Orders of magnitude is approximately equal to 1. So mixed convection, it's not really an equal sign, but in principle mixed convection is equal to natural convection plus forced convection, where both of these terms or any one of the two are not negligible. In terms of the Rayleigh number, the question is now, how do we get to the Nusselt number? And we do it by writing the Nusselt number equations as the heat transfer coefficient multiplied by a characteristic length. I'm still going to refer to this characteristic length quite a lot because it's very important. Is equal to a constant multiplied by, not Reynolds number, by Grashof number multiplied by the Prandtl number to the n. Grashof moment Prandtl. And because those two terms, with many of the empirical correlations and experiments, usually those two terms are next to each other. They are both non-dimensionalized values, and therefore we would refer to that as the so-called Rayleigh number. The Rayleigh number is just equal to the Grashof number multiplied by the Prandtl number. Rayleigh. But in general, you'll see that the C and the N are the things which is being influenced by the geometry of the surface, the orientation of the surface, the variation of temperature, and the thermophysical properties. And because we do not have the mathematical relationships for it, most of these values, the C and the N's, are being determined from experiments. And many of the experiments actually show that N is approximately equal to a quarter for laminar flow and in the order of a third for turbulent flow. And normally C is smaller than 1. Now I've said that I will come back to this characteristic length, the length, okay? There's not one rule that you can always use for which length to use. So if that is the case, how do you get that characteristic length? Well, there's more than one way, but the secret is you need to go and read the fine print. So typically in table 9.1 in your textbook, I'll come back, I'm going to come back to it just now. In table 9.1, different geometries is given. Typically a vertical plate like that, and then there's a Rayleigh number range, and then there's a Nusselt number equation. Typically for a flat plate like that. Then the next one is a plate at a certain inclination angle. Then there is for a rod or a circular tube, etc., etc. Now students are normally very easy or very good in getting this value and that value from the table. But the thing that they sort of miss is the most important thing in the table. The most important thing in the table. The most important thing is in the table is the characteristic length. They tell you how you must get the characteristic length for all the different geometries. So here, for example, it would be the diameter, and for that one it would be the length, that length there, and that diameter there. But then you'll get to ones where they say the characteristic length is equal to the surface area, for example, divided by L or P or something like that. You see that? So look in your textbook now to table 5.1. It's here on the PowerPoint. And there it shows the different types of geometries. Also, for these cases, which surface is being heated. And then here's the characteristic length. That one is equal to L, that one is equal to L, but that one is equal to the surface area divided by the perimeter. Okay, and there's the Rayleigh number range, the Nusselt numbers, and then there are three more geometries typically of which all the values are given like that. Okay. These geometries are just some of the simplest which are available in literature. There are many more, but if you are interested in other types of geometries, then you have to go and look in the literature for it. Something else that is also important is, just as previously with tubes, we have said that there are two different types of boundary conditions. Is the boundary condition on something like a plate or a tube or a sphere where the temperature on the surface is constant, and then there are boundary conditions where the heat flux is a constant. Normally, when we've got electrical heating or a nuclear reaction, then we've got a surface where the heat flux is constant. Now, the result of that is if we typically have a geometry like a flat plate, is that the temperature distribution will do something like this. So that distance there is an indication of the temperature. So that's for a constant heat flux, while this one would be something like that. Oh, no, sorry. It's the other way around. This is, of course, for a constant temperature. That would be the temperatures that remains constant. While for a constant heat flux, the temperature distribution is going to do something like that. And the problem is now when we get to the Rayleigh number or the Nusselt number, you will see that we need the viscosities. So the question is, at what temperature are we now going to use to determine the viscosities from? This one is very easy because you're going to use the surface temperature. But this one typically is a little bit more complicated, because even if you've got this temperature and that temperature, you do not know what this temperature is. So what do is you guess that temperature, and we call that temperature T L divided by 2. So you just guess a temperature, work through the problem, and then by looking at the heat flux and say it is equal to the heat transfer coefficient multiplied by Ts minus the temperature at L divided by 2. Because if the heat flux, it's a constant heat flux problem, so therefore it will be given. You're going to get the heat transfer coefficient from the correlation of the Nusselt number is a constant multiplied by a Rayleigh to the n. You're going to get it from there. And then, because you've guessed this one, you're going to determine Ts. Once you've got Ts, then you can guess a better value for T divided by L of 2 for that one, and you just do 1 or 2 iterations of this problem. It is not so complicated, and normally it converges very, very quickly. Something that you have to be very careful for in terms of the table, especially with the inclined tube like that, is that they are very specific in terms of which surface is being heated. And that determines which equation you should use. What's the reason for that? The reason for that is in terms of a hot plate, if it is now warmer than that of the atmosphere, and if that is a cold plate, so it is colder than that of the atmosphere, then this boundary condition or the velocity distribution here on the underside would do something like that, and on the cold side it would do something like that. But the other sides are much more complicated because it forms plumes. It forms plumes like this. And for this one, exactly the same. And those correlations are not given in your textbook. However, it is available in literature. Okay, that is some of the most important theory that we need for natural convection. Let's look at an example. The example that I'm going to look at is a tube or a pipe. Let's rather consider it a pipe. It has a diameter of 100 millimeters. Its length is 10 meters. Its surface temperature is 90 degrees Celsius. Surface temperature is 90 degrees Celsius. And then the question is determine the heat transfer rate. On a cold morning, when the outside temperature, T environment, is equal to 0 degrees Celsius. Okay, so on the outside we've got air. And we need to get the properties for air. If you go and look in your textbook in table A15, you'll get the properties there. And the properties is equal to a K value is equal to 0.02699 watt per meter Kelvin. Prandtl number is equal to 0.7233. The kinematic viscosity is equal to 1.772 multiplied by 10 to the minus 5 square meters per second. And this we got at a certain temperature. I'll be with you just now. And the temperature we're going to use is the film temperature, which is the average of the 90 plus 2 divided by 2, is at 45 degrees Celsius. There was a question there?
No, sorry, I just wanted to know what temperature you were going to use for the air.
Yeah, so 45 degrees Celsius I've got. So we've got the surface 90, environment 0, so we start with assuming an average temperature between the two. The one thing, if we look at the Rayleigh number, if we just look at this equation again, you can see that it would be possible for us, we've got the viscosity now, but we need beta. In the table, however, the values of beta are not given. Why? Because it's a gas, and therefore it is a good assumption to assume it's an ideal gas. If that is the case, then beta is equal to 1 divided by the film temperature. Okay, so help me in terms of what is TF, how are we going to calculate that? What is 1 divided by, which values should we use? Which value should we use for TF then?
45.
45, you all agree? 1 divided by 45. We have to be careful. It should be in Kelvin. Okay. So it is equal to 1 divided by 273 plus 45. And it is equal to 0.003145. Okay, we need to determine the Grashof number. The Grashof number is equal to G beta multiplied by Ts minus T infinite multiplied by the characteristic length to the third divided by the kinematic viscosity. Okay, so there is a horizontal cylinder. So those are the relationships that we can use. However, what is the most important information here? The most important information is that the characteristic length that we should use is equal to the diameter. And it's not because we just thought that that is the case, it comes directly from the table. Table 9.1 specifies that for us. Therefore, if we want to, we can maybe say the Grashof number based on the diameter is equal to G, which is 9.81, divided by beta, which is 0.003145, multiplied by the temperature of the surface is 90, minus that of the environment is 0, and the diameter is 0.1, it is 100 millimeters, divided by the kinematic viscosity 1.77. 1.772 multiplied by 10 to the minus 5 square, and if we do that, then the Grashof number is equal to 8.838 multiplied by 10 to the 6. Okay. The Rayleigh number is just a convenient way of putting the two together, the Grashof number and the Prandtl number. The Grashof number is equal, I'm not going to write it down, the Grashof number, there's the value. The Prandtl number, there's the value, 0.7233, so that works out as 6.393 multiplied by 10 to the 6. We have to check it in the table in terms of which range it is valid for the equation. And in the table, it tells us that the Rayleigh number must be smaller than 10 to the 12. So we are fine. Okay, so the range is okay. If we do not fall into this range, you have to go and look at literature to get the specific details. The equation that they give is the Nusselt number is equal to 0.6 plus 0.387 multiplied by the Rayleigh based on the diameter to the 6, everything square, divided by 1 plus 0.559 divided by the Prandtl, everything to the 9 divided by 16, and then everything underneath to the power of 8.27. And this is equation 925 in your textbook, which is in the table. Right, I'm not going to put in all the values here on the board. It's very simple. There's the Rayleigh number. Okay. Prandtl number you've got, so you need to go through the calculation, and the result of the Nusselt number calculation is a Nusselt number of 24.83. The Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length. The characteristic length would now be equal to the diameter. The Nusselt number is 24.83. It's equal to the heat transfer coefficient multiplied by the diameter divided by the thermal conductivity, and the thermal conductivity is equal to 0.02699, from which we can determine that the heat transfer coefficient is equal to 6.701 watts per square meter degree Celsius. It's also quite important that when you start doing all these calculations, you take a look again at chapter 1. In chapter chapter 1, where the concept was introduced the first time of the heat transfer coefficient, they said something very important. And that is that in natural convection, the heat transfer coefficients are normally low. Typical order of magnitude is about 10. Okay? Then when you've got forced convection, typical heat transfer coefficients, order of magnitude of hundreds to 1,000. And when you've got two-phase flow, like condensation or boiling, order of magnitude is 10,000. So now if you remember that and you calculated, for example, this heat transfer coefficient as 6,701, then the red lights should go on. Okay, so order of magnitude about 1. Anything up to 1 to 10, 20, 30, 40, those are the typical order of magnitude of heat transfer coefficients. Right, now we can determine the heat transfer rate. The heat transfer rate is equal to the heat transfer coefficient multiplied by the surface area multiplied by Ts minus T infinite. The heat transfer coefficient is equal to 6.701. The surface area is the surface area through which the heat transfer occurs. So it's this outside surface area. It is equal to pi multiplied by the diameter, which is 0.1, multiplied by the length, which is 10 meters, multiplied by the temperature difference, 90 minus 0, and the result is a heat transfer rate of 1895 watts, and that is approximately 1.9 kilowatts. Take a look at it. Tell me if you're comfortable with it, if it looks okay. It's important, this value, because it gives you an idea of what would the heat losses be if you've got an uninsulated pipe and there's heat transfer to the environment. You happy with the answer? I was hoping that there would be somebody saying no, we forgot something. And yes, it is true, there's something else that we didn't take into consideration, and that is radiation heat transfer. That is the other chapters that you're busy with. Let's go and check the radiation heat transfer now. So this heat transfer rate, I would like to change it and say that is the convection heat transfer rate. Let's go and check now the radiation heat transfer rate. That is equal to the emissivity multiplied by the Stefan-Boltzmann constant, the surface area multiplied by the surface area to the fourth minus the environment temperature to the fourth. And they didn't give us the emissivity because that would have given us a hint of that we should take the radiation heat transfer into consideration, but let's assume it is equal to 1. The Stefan-Boltzmann constant is equal to 5.67 multiplied by 10 to the minus 8. The surface area through which the heat transfer occurs is pi multiplied by the diameter multiplied by the length of this tube multiplied by the surface temperature. And now we have to be careful. It's the surface temperature in Kelvin. 273 plus 90 to the power of 4 plus, of course, 273 plus 0 to the power of 4. And the heat transfer rate through radiation is then equal to 2,103 watts. So if we compare it to the convection heat transfer, the radiation heat transfer is about the same order of magnitude. The emissivity, of course, would not be equal to 1. It would be a little bit smaller than 1. But we can see we are talking of about the same heat transfer rate. So if we therefore look at the total heat transfer rate, which is then equal to 1895 plus 2103, then that works out as 3,998 watts, which is equal to 4 kilowatt. 4 kilowatt of heat losses to the environment. You happy with that? Right. Another type of category of problem is the flat plate. And in this example, I would like to look at a flat plate with the dimensions of 700 millimeters and 900 millimeters. And this flat plate is insulated on the one side with a surface temperature of 100 degrees Celsius. And the environment temperature is 20. And we're going to look at the influence of different configurations. So imagine this is a flat plate. Okay? It has been heated to 100 degrees Celsius and the outside temperature is 20. So if we keep the flat plate like this, there will be natural convection to the environment. But now my question is going to be, what happens if you change it into this direction? Okay. And then, okay, the heat transfer is only from this one surface. So heat transfer like that, then like that, and then like that. Which one will be the most? Would you like to vote? The one going up, who votes for that one? One like that? Okay. The one like that? Okay. Let's see. So we are going to do the 3 different orientations. So the first orientation, if I can show it schematically, is vertical. Then the other one is going to be the heat transfer going in an upward direction, and for this one going in a downward direction. So we can show the heat transfer rate like that, going up like that, and then that one going like that. Heat transfer facing down. So those are the 3 possibilities. Right, let's start with the vertical plate. The vertical plate, we've got a film temperature, which we're going to say is the average of 100 plus 20 divided by 2, and that is equal to at 60 degrees Celsius. So we would like to get the air properties at 60, and those are a K value of 0.2808 watts per square meter degrees Celsius. That's the K value. There's the Prandtl number is equal to 0.7199. The kinematic viscosity is equal to 1.92 multiplied by 10 to the minus 5 square meter per second, and beta is equal to 1 divided by 273 plus 60. If we look at table 9.1, that table there we can see the one side is insulated, there's the characteristic length, there's the Rayleigh number range, and there's the Nusselt number equations that you can use, 3 of them. So let's start by calculating the Grashof number. The Grashof number is equal to G multiplied by beta, the temperature difference multiplied by the characteristic length to the third, characteristic length, divided by the kinematic viscosity square. And that is going to be equal to 9.81. Beta is 1 divided by 273 plus 60. The surface temperature is 90. The environment temperature is 20. And very importantly, in the textbook, they show that the characteristic length is L, and in the sketch that is equal to L. You see, 0.9 meters. So that is 0.9 meters. Divided by the kinematic viscosity, which is equal to 1.92 multiplied by 10 to the minus 5. And the Grashof number is now going to be equal to 2.192 multiplied by 10 to the 9th. To save time, I'm going to skip a few things now in terms of calculations. So the Rayleigh number is equal to the Grashof number multiplied by the Prandtl number. Very simple. There's the Grashof number, there's the Prandtl number. Okay. And then, in terms of the calculation of the Nusselt number, it is equal to 0.825 plus a long equation of the Rayleigh number here at the top, etc., to everything like that. And that is equation 921 in your textbook. It appears in the table. Of course, you're going to select this equation based on the Rayleigh number range and make sure that the range is okay. And the result is going to be a Nusselt number of 141.8. So the Nusselt number is equal to the heat transfer coefficient multiplied by the characteristic length divided by K. Characteristic length that we need to use there is 0.9. Can go and determine the heat transfer coefficient as 5.687 watts per square meter degrees Kelvin. It's a typical value that we would expect, not 50,000 or something like that. Can calculate the heat transfer rate through convection. It is equal to 286.6 watts. As we've done in the previous problem. The area is going to be, of course, 0.9 multiplied by 0.7. Go and calculate the radiation heat transfer, and the radiation heat transfer is equal to 428.2 watts. And therefore, we can calculate the total heat transfer rate as 714.8 watts. Okay, let's change the orientation to horizontal. It's insulated there, and the heat transfer rate, the heat transfer can only occur into the upper direction. Again, the Grashof number is equal to G beta, Ts minus T infinite, multiplied by the characteristic length, like that. But now you have to be careful. The characteristic length is now equal to, what does it say in the table? For a horizontal plate, there it is. So we are looking at this first configuration. The characteristic length is equal to the surface area divided by the perimeter. Surface area divided by the perimeter. The surface area is equal to 0.9 multiplied by 0.7. And the perimeter is 0.9 plus 0.7 plus 0.9 plus 0.7. 2 times 0.9 plus 2 times 0.7. And then the characteristic length is now much smaller. It is equal to 1.1969 meters. You see that? In terms of the Nusselt number calculation, now the Nusselt number is equal to 0.15, rally to the third. Why not this long equation? Because the table tells you which equation to use. Okay. And that is equation 923. Okay, you can go through all the calculations. I'm not going to have time to do it. The convection heat transfer is 351.1 watts. The radiation heat transfer is 428.2 watts. And the total heat transfer rate is then equal to 779.3 watts. Okay. That is the second configuration. The third one is, it's insulated there. The heat transfer rate is now in that direction. The characteristic length calculation is exactly the same, but now we need to calculate now we have to use the equation. The Nusselt number is equal to 0.27. Rally to the fourth based on the characteristic length, and you can go and do all the calculations and check and see that the total heat transfer rate is now going to be 577.6 watts. Okay. Therefore, the configuration that is going to have the most heat transfer rate is going to be that one, the vertical one. Okay. Right, ladies and gentlemen, thank you very much. Enjoy your long weekend, and then I'll see you again next week.